great pleasure to. Okay. Oh, and Padhraic, is it okay if we release this recording afterwards?
Sure. I'll try to temper my comments and not say anything too controversial.
Oh, do, Padhraic, do. So yeah, it's a great pleasure to introduce my fellow countryman, Padhraic Smyth. Well, we originated in the same country, but we ended up in two different ones. I'm in physical sciences, he's in computer sciences. Padhraic is a chancellor's professor here at UCI. He was the founding director of the UCI Center for Machine Learning, and also a founding director for the UCI Data Science Initiative. He's received funding from every possible agency you can imagine, and from most high-tech companies you can imagine. He also does lots of consulting and has served as scientific advisor for some of the competitions. He grew up not so far from where I grew up, in County Mayo, and he went in the west of Ireland, but I grew up on the east of Ireland, so there's a certain tension and rivalry there. He got his degree in electronic engineering at National University of Ireland in Galway in 1984, and then got PhD degrees in electrical engineering from Caltech, master's and a PhD. So he was at JPL for about 10 years after that, and then has been at UCI since 1996. And today he's going to give us a proper education in the statistics behind machine learning, which is a really important subject. Take it away, Padhraic.
Thank you, Kieran, for the nice introduction, and thank you, Kieran and Domingos, for the invitation to speak to physical sciences. I've been at Irvine now since 1996 and have enjoyed multiple connections with your school over the years. Most recently, we've just finishing NSF training grant, and many of the grad students interested in machine learning have participated in our program, and many of the professors have been advisors for students. Daniel Whiteson is a co-PI, Jim Randerson. And on the research side, I've had, particularly with earth system science, kind of emanating from my original days back at JPL, lots of joint projects that I've enjoyed a lot over the years. So very happy to share what I know. And I decided to give rather than a deep research talk, more of an overview talk on connections between deep learning and statistics. And I'll say a little bit more about that in a minute. All right. So what I'm going to do is I'm going to start off essentially assuming you don't really know much about deep learning. So if you do, you may be a little bit bored, but hopefully not too bored. And we'll take an optimization perspective, because that is a lot of what deep learning is about, and machine learning in general. And then we'll establish some links from the optimization perspective to statistical thinking. And we'll see terms like likelihoods and distributions and Bayesian approaches, and we'll see how they work their way in essentially implicitly into the optimization that we're doing with models like deep learning. And then towards the end, I'll talk about some of the current limitations of deep learning that I think are important to know about. You know, deep learning is a very useful tool, but it's not a magic bullet and has certain limitations. All right, so some caveats up front. I'll be focusing on predictive modeling. I'll say a little bit more what I mean by that, but I won't be talking about things like unsupervised learning, say clustering, reinforcement learning, adversarial learning, attention-based methods, et cetera, et cetera. However, a lot of what I'd say will apply to those techniques as well. So I've picked predictive modeling because it's by far the most widely used technique at least in computer science and machine learning. And I will focus on classification, but a lot of what I say is relevant to regression and time series modeling as well. I'll probably interchange terms like machine learning and deep learning going along. You know, it's kind of a joke among machine learning people nowadays that machine learning is deep learning, but there are parts of machine learning that don't involve deep models, alive and well and very useful. Not everything needs to be a deep network. And apologies at the end, I have presented these slides over the years, last few years, in different sort of combinations, variations of these slides, this talk. I keep coming back to it because people tell me it's quite useful and interesting. So, but if you've seen some of this before, well, I won't mind if you log off or don't pay attention. All right, so some notation, predictive modeling setup. We're going to have training data. If you're a machine learning person, you always start with thinking about data. We'll talk later about where that might come from. We have, hopefully you can see my mouse here, vectors. Subscript indicates the index over which training data pair we're looking at. So the inputs are usually high dimensional vectors. You could imagine pixels. And the y's often are scalars. Just they could be vectors too, but usually scalars. If they're real valued, we call it regression. If they're categorical, see a typo here, classification. So this is the setup. We've got, maybe this is in the form of a big matrix, with a lot of columns for the x's, a lot of rows for the n data points, and another column of target values y's that we want to predict. Okay, so we're going to spend some time talking about this, and of course, what we want to do is build some kind of model, and it's going to be, again, predicting y, so it'll be scalar valued. We can think of this as y hat, but it's going to be a function of the inputs, and it'll have some parameters. And people use different names for these parameters. If you're a statistician, you use the word parameters. If you're a deep network machine learning person, you might call them weights. But they're essentially, at least mathematically, much the same thing. So we can think of this as some kind of black box that will take in an input x. It's parameterized by theta, and it will pop out a y hat. And of course, we want to, on the training data or on future data, be able to predict as well as possible. So I'm going to use this equation quite a lot. So we'll kind of step our way through it here, and in terms of learning a predictive model. So the first term we look at, don't worry too much about the complexity of this for a minute. Here we have that f function I just talked about. This is our black box model with so far free parameters theta that we haven't determined yet. So it's going to produce a predicted value for the ith input here, the x that is the ith input. And then we're going to compare that, go the right direction here, with the desired target. So this is from our training data. So we're making a prediction with some values of our parameters, and we're comparing that with y hat. And the way we're comparing it is through some kind of loss function. So if y and f are both real valued, then squared error is the most commonly used loss function for real valued data, but there's a lot of other possibilities. So I'm leaving this unspecified. We'll just talk about this capital delta here as some kind of loss function, scalar valued loss function. And then we're going to sum that over all of our pairs of examples. We could also take an average. We'll do that later. And so this is term on the right here is, we can think of it as our total loss. And we'll think of it as a function of theta. And the reason we do that is, we're going to fix the functional form of the model. Our x's and y's are now, given to us, or we've determined them by an experiment. We've gotten the data. We've specified a loss function, and we'll talk about how to do that. So the only thing in this equation that we don't know is the parameters of the model theta. So we're trying to minimize this whole expression, this total loss, as a function of theta. So this is where optimization comes in, is optimizing. How do we optimize this term on the right? We'll spend some time talking about that. And so if you think about it a little bit, there's a few key components here that pretty much every predictive modeling problem has. You get some training data. You then specify the functional form of the model that you want to fit. Maybe maybe you combine a few models, but generally speaking, we'll think of some particular form of model. We need to specify a loss function in that equation we just saw, and then there's the actual optimization method, the algorithm that we use to minimize this loss function. And we'll talk about all of these elements in the next few minutes. And essentially, how we change, if I change the loss function or change the model or change the optimization, well, if I'm a machine learning researcher, I get another paper. There's all the possible combinatorial combinations, although we try to then group them into families so we don't write millions of papers, but you can break down a lot of predictive modeling papers and methods into combinations of these things. One thing I'll point out is that everything we've said so far, there's no probabilities, no statistics. It very much looks like an optimization problem, and we'll keep that perspective for a few minutes and then sort of work our way into the statistical angle. All right, so the very first thing is the data, the training data. I won't say much about this. This is what we defined before. We have some data because in machine learning, there's kind of an assumption the data are given to you, and they're also an implicit assumption, as we'll see in a few minutes, that these are actually random or IID samples from some unknown underlying distribution that's governing the phenomenon of generating X's and Y's in whatever problem we're looking at. And this is often a bit optimistic, particularly the part about that, the future data will also be coming from the same unknown distribution. But it's the typical assumption. And there's relatively little work in machine learning on, going and getting your own data, like doing experimental design as you might in statistics, or running an experiment as you might in physics. If you talk to a machine learning student or professor, they'll say, oh, I don't know how to get data, just give me the data. That's typically the setup. So there's often, what's called opportunistic data, data of opportunity that just happens to be there. A satellite has this data, let's analyze it, rather than doing experiments to create data. So the functional form of the model that we're going to use. Now this is a vast space. There's a lot of mathematical functions we can use. Let me try to give you a little bit of a characterization of some of the more common types and how we end up at deep learning. So let's start off here. Now I'm going to use subscripts here to indicate different components of the input vector. So X is our input, an example, it's a vector. These might be pixel values, and there's D of them. Remember, D can be pretty large in our problems here. And so our function takes in X and some unknown parameters theta and produces a number. And over on the right here, we have the simplest possible model you could think of, a linear, at least linear in the inputs. For every X, there's a theta, a weight or a parameter. We sum these up. We're also going to need an intercept just geometrically, otherwise we won't have full flexibility. So that, we learned this, most of us in secondary school or high school, fitting a simple linear model, but actually quite useful. A lot of useful stuff over the years been done, somewhat interpretable. So this is kind of our starting point. Just sort of a side note, we can do linear parameters. This is still a linear model. If these G functions, let's say I take powers of X or cross products of X or some other functions of X, as long as they're predefined, then this thing is still linear in theta. So that is also considered a linear model. There's a concept in statistics that's quite useful called a generalized linear model. And what you do here is you build your standard linear model, but you put some nonlinearity on the end of it. I won't go into details, but it's quite a flexible general family. And in fact, it has some connections to deep networks. So let me motivate that by talking about the problem of classification. This is probably the single most studied problem in machine learning. And in classification, our Y value now is not real valued, but it's categorical. It takes one of K values. So, you're classifying images. Is it a cat? Is it a dog? Is it a human? And of course, you need at least two values. So K could be 2, but it might be thousands for some image classification problems. And typically what we want to do here is learn a conditional probability. Our function now is actually producing, it's going to produce K probabilities at the output, one for each possible value of Y. And there's a vector conditional probabilities that sum to 1. And so we might ask the question, if we want to use the simplest possible model here, will linear function work? Could we use a linear function to model these? And of course, the answer is no, because we need to scale these to be between 0 and 1. And the linear function, if we have negative weights or negative inputs, could end up anywhere on the real line. And so the very simplest sort of way to get this to work is to take a linear function and push it through some kind of scaling function that will take the real line and map it to 0, 1. And this, the logistic function, or what neural network people call the softmax function, does this. And so what we have here is what's called a logistic model. It's a form of a generalized linear model we saw on the previous slide, and actually a very useful model, widely used in industry for a lot of problems. And we're using it here as a building block to kind of take us towards neural networks, but it's a very useful building block along the way. And if you remember nothing else about logistic regression, it's a linear model with a nonlinearity on the output to get probabilities. We can start to draw these pictures, look at these pictures that pop up in neural network papers and books, that we can look at our logistic regression model or logistic model now as a more like a block diagram. And what are we doing here? Well, there's 3 inputs. There's our constant offset. So we'd have 4 weights. And this is the little nonlinearity that softmax logistic function that's going to squish the real valued weighted sum of the inputs. There's a weight on each edge here, and we get a scalar output that is between 0 and 1. And we can, in this case, there might be just a 2-class problem. We just need one probability. What's the probability of Y equals 1? So this network, it's really just logistic regression. Each edge has an associated parameter. And if you were back in 1960 and doing neural networks, and people were on computers, these were the types of networks people were looking at, perceptrons. These were considered the very first artificial neural networks. So if you don't go quite far as back in time, if you go back to the late 80s, 1990s, when I was starting out, there was a second wave of neural network research where essentially you could think of it as combining multiple logistic models. So here we have in this picture 3 different logistic models. Remember before, this is a logistic model. Here I've got 3 nonlinearities, each of which has a weighted combination of the inputs coming into it. And the weights are going to be different. So each of these logistics is sort of tuned to pull out a different, if you like, feature of the input. In this case, only a 3-dimensional input. And then we're going to take those 3 features, if you like, that have been extracted from the 3-dimensional input space, pass those along, do another logistic layer here, and produce an output. And this middle layer here is called the hidden layer. And it was, naturally, it's a much more expressive function, this as a mathematical function, compared to just a single logistic on its own. And this, was the basis for a whole set of neural network research back around the 1990s. People actually knew you could go to the next level back then. You could do the following and go deeper. So instead of a single hidden layer, you could have 2 hidden layers. You could sort of recursively compose these architectures, if you like, and make them as complicated as you want. Now, naturally, there's a lot of design decisions here. How many hidden layers, how many of these hidden units of each hidden layer, and that's still an issue. How do you figure out? It's somewhat done computationally through trial and error, essentially. But you get very flexible, highly nonlinear functions, and this can become very complicated with modern deep learning, as many of you know. So let's just look at what's actually a relatively simple example for digit recognition. So here the inputs are pixels. So this is written out as one long vector of grayscale pixels. The outputs are 10 probabilities. Is it a 0, a 1, or a 9? And in fact, this type of model is used by the post office when people used to use post offices and send things called letters to each other for handwritten zip code recognition, one of the early successes of neural networks. Now, all this stuff in the middle, don't pay attention to the details. This is a feed-forward neural network. It has things called convolutional filters in it, but it's a function. It's a mathematical function. We can differentiate it with respect to its parameters. And the key thing is we can learn all of these different filters and weights and so forth using data. We can optimize them using that loss function I talked about before. So if we think of this whole thing as a black box, takes in pixels, produces probabilities, and the thing in the middle here is our black box F function that we talked about before. And now the thetas are lots and lots of different parameters associated with different parts of this thing. You can go crazy with these networks, and people have. And for problems like image and speech and text, where you have huge amounts of data, particularly in industry, people have built massive models. This is actually, relatively small by modern standards. From a few years ago, a Google image recognition network, 27 layers, millions of parameters. The pixels are all over here. Here's the outputs, the class labels, and lots and lots of different layers. These are all essentially little logistic units in a sense, but many of them higher dimensional, different types of links. And you might wonder, how do you come up with this? Well, if you're Google, you hire 50 engineers and you pay them a lot of money and set them to work for a year or two exploring different models, and then they produce this. But the key thing to keep in mind is it's still a function from a sort of a first principles point of view. The X are the pixel inputs. Theta are all the different parameters in this network, and we're going to try to optimize these, and we can, which is one of the successes of deep learning. But now theta is, instead of that sort of simple linear model we had earlier with one weight per input, now it's in the millions, millions and millions of parameters. So it can be hard to figure out what's really going on here. So here's one way that helps me at least to think about this. So this is a picture of a, sort of a neural network with inputs and outputs, as we've been seeing. This, I forgot to give credit here. This is from Trevor Hasty and Brad Efron at Stanford. Very nice book chapter that they have on deep learning and statistics. And I think what's useful is that we can think of, the early, in fact, right up until the second to last layer of the network is essentially doing feature extraction. And I'll say a little bit more about this in a minute. And then the final layer is usually something like a logistic model, or more generally, a generalized linear model. So, if I were a statistician and I say, well, I know how to fit generalized linear models, and my friend is a neural network person, the neural network person you could think of as, doing feature extraction in a very clever way on very high dimensional inputs. And then you take those features and you push them through your statistical model, if you like. So the very output layer looks like a statistical model. Now, the key thing here is you do the whole thing at once, simultaneous. You learn all of this in one go, rather than first doing feature extraction and then fitting a statistical model to the features. But there's that idea that part of this is extracting features from high dimensions, but part of it involves fitting of statistical models. And we'll go into that in more detail. So what are these hidden representations, these neurons in the middle, these hidden units extracting? Well, one really successful example is essentially just little templates, say for spatial data, for image data. So, a lot of you will be familiar with, like edge detectors or filters you can apply to an image. Here's an example of a, vertical edge detector. The key idea in deep learning with image data is not to pre-specify these filters, but to learn them in a predictive fashion. To make these will now become weights in our neural network, these values, and we will let the network learn whatever filters it needs to learn to predict the output. And this has really changed areas like computer vision dramatically, from where people used to handcraft features to now this is done with large data sets. In fact, not just in vision, but in speech, natural language processing, the same pattern, machine learning up until about 5 or 10 years ago. And I remember this well because I was doing it, and some of you might too. You would have to figure out sort of, how do I do feature extraction from my pixels? And then I do some kind of pre-processing. And then eventually I build a classifier or statistical model. But the whole thing is done in different stages. It's not coupled together. It's suboptimal, very time consuming, very manual. Same thing with speech, same thing with NLP. And now, the idea is that we can do all of this in one go without having to pre-specify our representations. We can also do this with temporal data, for example. So I'm just very briefly mentioning recurrent models here. You can think of each block here as mapping some inputs to output, X to Y. Here's the hidden layers. If you ignore these arrows, each of these could be doing a sort of an instantaneous prediction, t-1, time t, at time t+1. The key idea with recurrent networks is to link the hidden representations over time. So if we look here, for example, at t+1, if I want to predict yt+1, given some maybe high dimensional input, I can also bring in information from the past in some flexible way. And then again, all these arrows are parameterizable weights that can be learned. So if you have enough data, this works well and has been found to be very useful in areas like speech and text in particular. So this gives you rich sets of functional forms. And there are models like this in applied mathematics and statistics, state space models for time series, but this kind of enlarges the space of models we can think about. Before I go on, let me stop for a minute, since I could be talking to an empty audience here if I don't check and see if there's any quick questions at this point. I'm assuming people can hear me, see my mouse. Okay, I see at least one person nodding. All right, let's keep going. I don't hear any urgent questions. This is a nice opportunity for a very brief detour on the history of neural networks, some of which I've said already. The perceptron era was the first wave, 1950s and 60s, just with those linear models that I talked about, or essentially the logistic model, maybe a hard threshold instead of a soft threshold. And then Mervyn Minsky at MIT came along and proved some theorems that perceptrons had limited representational power. In other words, there was a lot of functions you couldn't represent. And this actually had a huge impact on the field. Funding agencies stopped funding, and people realized you needed hidden layers. But back then, they didn't really know how to put it all together and do what we call gradient descent in a few minutes to get this to work. And then in the early to late 1980s and through the 90s, there was a second wave of enthusiasm among researchers. Backpropagation is essentially a gradient method for training models with hidden layers. And there was wild enthusiasm. It was really, people were just, okay, pattern recognition is solved. conferences, funding, lots of stuff. But the enthusiasm died out because once you add more than one hidden layer to these models, it turns out they're quite hard to train. And the computers at the time just weren't up to it. There wasn't enough data. Some of the tricks for optimization weren't known. So it's interesting. Things fell out of favor. A few people, Jeff Hinton, Yoshua Bengua, Jan LeCun, among others, persisted and said, no, neural networks are really useful. Let's keep researching them. But many of us said, there's other things we could be doing. We turned to other models. And then, the last 10 years, deep learning has come back in neural networks in a big way, particularly deep networks. This is essentially the third wave. And now it's practical computation to train these models with larger data sets. And we have better optimization tricks and techniques. And there's also sort of a momentum aspect. More people are working on it, so there's more progress and so forth. And this has got us over the hump in getting these models to work. All right, that's the side story of the history. Let's come back to the problem that we started with, which was minimizing this loss function. So we're still looking at this as an optimization problem. We've just spent some time talking about the function f and the different options we have. We started off with linear functions, then logistic, generalized linear models, and then we went to single hidden layer neural networks, and then deep networks, very briefly. But that means we have a lot of options in choosing this f function. The next thing we're going to look at here is how to choose the loss. We'll just briefly talk about that. So that's sort of our third component of the problem. So I mentioned before, squared error, if you're doing regression, very standard, very classical. There's another one that's very widely used if you're doing classification. So remember, for classification, y can take one of capital K values. So we need K probabilities. And the loss function you use here is a little odd to look at if you haven't seen it. It's log of 1 over the probability that the model is assigning to the true class given X, the observed class given X. So how does this work? Well, we're trying to minimize this thing. So let's say we get it perfectly right. We get 1 over 1. I'm going to get log 1, I'm going to get 0. So that's, if everything is positive, then that's certainly going to be a minimum. If this is very small, if I say I'm very small probability to what actually happened, then 1 over a small number is a very big number. I get log of a big number. So this seems to be working in the right direction. It's going to encourage me to put high probability on the classes that actually happened in the data, the ones that I see. And it turns out it has all sorts of nice properties. It's not an arbitrary function. It turns out it really has nice theoretical properties. And so it's the one that people use by default for classification. All right, so we'll come back to that loss function, say a bit more about it, but those are the two that you're going to see a lot in sort of software and code for deep learning. Moving on, we now have, looking at optimization methods. The final piece of the puzzle here is how do you actually minimize this function? So here's our equation again, which you're probably getting tired of looking at this point. And remember, the goal is to minimize this as a function of the unknown parameters, all those weights in those big neural networks. Very high dimensional problem. This is a scalar value function of a very high dimensional vector. And we can't look at this function. We can't plot it. We can't do grid search. Impossible, way too high dimensional. So what kind of optimization method do we use? There's lots of books and textbooks and papers on optimization, many different ideas. So one key idea in optimization is the difference between convex optimization and non-convex optimization. So convex optimization, let's say we only had one parameter theta. Here's our L of theta that we're trying to minimize. It means it's a relatively straightforward optimization problem. It's a convex function as a function of theta, has a single global minimum. So if we're doing gradient methods, gradient tells us, we start somewhere. It tells us which direction is uphill and downhill. So we go downhill and we'll eventually, we might overshoot. If we take small enough steps, we'll arrive there. And examples that are convex in terms of our loss function, if f is a linear model and our loss is squared error, then we get a convex L of theta. The logistic model and the log loss also turn out to be convex. So a very nice feature of those models. Logistic regression is very easy to fit for this reason. Unfortunately, most machine learning problems are not convex, and you get the non-convexity with the combination of the f function and whatever your definition of loss is. But very few of them are convex. These are some exceptions. And so the non-convex optimization, we just assume our functions look something like this. We don't actually know what they look like. There's some theory, but it's very difficult because theta is very high dimensional. And this function changes every time we get new data and change our model. So it's very hard to say much about it in general. This is a really hard problem, really hard optimization problem. There's many local minima, many places that are suboptimal. Here's in this case, the global minimum. And this is the rule rather than the exception. Remember, theta is really, we'll say it's P for the number of parameters, P dimensional, and P could be 1 million or more. This is not unusual in fitting neural networks. And so the optimization methods that are used are surprisingly simple. Just gradient descent. It's essentially heuristic. You start somewhere randomly and you go downhill with small steps. You compute the gradient and keep going downhill. Now you may end up at local minima. By and large, with large networks, it seems to not be a problem, but this whole area is rather heuristic and a little unsettling that all our networks are trained by this very simple method that is subject to finding local minima. So gradient descent, I won't go in details into the equations, but you take wherever you are currently in parameter space, you compute the vector gradient. This goes uphill, you want to go downhill, so you go the other direction in vector space. You scale up by a small amount because that's downhill where you are. If you go too far, you might not actually be going downhill, and you get your new updated parameter vector. So these simple gradient methods are the workhorse of machine learning in general and deep learning in particular. And you might say, oh, why don't we use, sort of better iterative methods like second order methods, second order information about the gradient? Well, remember P is, maybe 10 to the 6. We've got to invert that matrix to figure out the, basically to get what we need, at least square it. It's going to be completely impractical to do that. So first order gradient methods. Now to compute this gradient, we have a sum, our total loss, we're computing the gradient of the loss. It's expressed as a sum. It has some structure to it, sum over the data points. So what we're doing actually is computing the gradient of every data point and then summing them up. And if we think of the computational complexity of this, it's going to be at least order n, because we're summing n things, times the gradient for each individual data vector in our training data. And that is going to be, at least order P. Let's say it's order P. So, and P is very large, number of parameters, number of weights. So P times n, maybe n is 1 million images, could be a lot more in some large scale applications. Maybe theta is 1 million. That's 1 million times 1 million, 10 to the 12, just for one gradient, one step. And you may have to do many of these. So gradient methods, full gradient methods are actually very slow with deep learning. And so what really made deep learning work and makes it work in practice is the notion of stochastic gradient. Very simple idea. It says, well, this is all a heuristic anyway. So why don't we just approximate it? Let's find some random sample of data points, and we just use those to compute the gradient instead of the full gradient on everything, since this is really heuristic search to begin with. And you scale it appropriately. You could even pick one data point and just go downhill based on one data point. Well, you might end up going uphill for the overall thing, but on average, you'll end up going downhill. So you're really approximating the full gradient. But it turns out if n is large, m can be much smaller than n, and you're making many fast, sort of noisy updates. In fact, you can sometimes converge before you see all of the data. So that's sort of sublinear convergence. What's going on here? Well, visually, if we think of a two-dimensional problem, imagine this is our surface and we're sort of near the bottom of this bowl here. So full gradient, is diligently going downhill locally. These are the red dots, but taking maybe forever to compute each direction, each gradient step. The stochastic gradient is these much noisier steps, should have started here. And it may actually go uphill some of the time because it's noisy, but we're making a lot more of these steps, many, many more of them. And the theory tells us it generally will work under fairly broad conditions. It's actually an application of a very old idea from Robbins Monroe back in the 1950s. So it's not really something inherent to deep learning. It's just doing what machine learning people do very well, which is borrowing ideas from other places and scaling them up to massive data sets. And actually an interesting side note is if you're fitting statistical models, not deep networks at all, just like some kind of generalized linear model and some large data set, this will work there too. You can scale up statistical models with stochastic gradient, a very nice way to use statistical models on large data sets. All right, so we've talked about optimization. We've talked about pretty much the functional forms, the loss functions. Let's start making some connections to statistics here. So because everything up to this point is totally optimization. There's been nothing statistical, no probabilities except in side reference. So let's look at the squared error loss, for example. And I'm going to basically tell you that what we're actually doing to minimize this loss is we're actually maximizing a likelihood, which is a traditional statistical thing to do. So let's look, here's the definition of the squared error loss. We've plugged in squared error now for our loss. We're summing over all the training data points. This is some function of theta, some black box. if we rewrite this in a different way, if I take a Gaussian model, predicting y's given a mean that varies as a function of x with some fixed sigma squared, this will have an exponent that looks like this, a negative of this. If I take the log of that, the log likelihood for a Gaussian data model looks exactly like this. So in fact, we can work our way in either direction, from the squared error loss function to a conditional log likelihood of the data, actually the negative of it, they work in opposite directions. Or we can start here and work our way back to this loss function. They are, from an optimization perspective, they are the same. There's a few constants missing. Sigma squared didn't show up from our optimization perspective, but it's effectively in there. And this gives us a direct equivalence, which is pretty cool, that, Fisher back in 1912 proposed maximum likelihood for relatively simple models back in those times without computers, but the same principle is being applied to our big deep learning models. When we minimize a deep learning model, if this is a deep learning model with squared error, we're actually maximizing a log likelihood. And because this is a negative, so this is the log likelihood, minimizing this is equivalent to maximizing this, all happening as a function of theta. So this is very cool. It also happens for that log loss that I showed you before. Here's the definition of log loss. Again, we look at the negative of it. This turns out to be what's called a multinomial likelihood, well-defined likelihood term in statistical modeling. And so we're doing likelihood maximization when we're minimizing this. And this was very useful to learn early on in the days of neural networks. In fact, statisticians showed up at our conferences to kind of tell us what we were doing back in the 1980s and 90s. Why is this useful? This allows us to link deep learning loss functions with classical well-known ideas in statistical estimation. As I've said, these loss functions are equivalent to parametric log likelihoods, Gaussian, multinomial, things like that. And interesting things start to pop out. That summation that seemed pretty innocuous in our loss function actually it's corresponding to independence. When I take the log of a likelihood, if it's a product of terms, I'll get a sum of log terms. The product there represents independence. So that sum we're effectively with our loss functions assuming that all of our training examples are independent rather than, say, some kind of Markov dependence. And another thing that this allows us to do now is to link our training of deep learning to Bayesian ideas. And we can think about Bayesian deep learning because our loss functions are in effect log likelihoods or negative log likelihoods. So we can work backwards. We can start with log likelihoods if we want to think about our problem in a statistical fashion and derive appropriate loss functions to train deep learning problems for different problems. And this is something that I'm not sure a lot of people are fully aware of. So if you have a different noise model in your problem, as physicists who understand noise pretty well might have, you can go beyond Gaussian noise. You can have Poisson noise, exponential noise, and essentially you have a GLM type likelihood, but it changes the loss function that you train on. You can also introduce dependence. You can put in autoregressive, Markov, other types of data dependencies and get extensions, but it gives you a principled way to develop loss functions that have well-known properties. So this is a very nice connection. There's some other things that we can become aware of. And now we're moving into, what I'm doing right now is telling you, we take this optimization perspective, which is up here, and now we're going to link it to ideas in probability and statistics. So let's normalize our sum. We put a 1 over n out here. This doesn't change the shape of the function. It just means essentially we're computing an average. So I have L prime here. Now, if I think about this looks like this is a bunch of samples X and Y of some, loss. So it looks like an expectation, and in fact, it will, if the data are random samples from some unknown underlying distribution on X and Y, and as n gets large, asymptotics, blah, 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 this is just an empirical estimate of the expected value of this loss between Y and f of X with respect to the joint probability distribution of X and Y, which we don't know, but it's what we're assuming is generating our data. And further, if we break this down a bit more, this turns out, we can use kind of expectation properties to break it into two parts. An inner expectation, if I fix X, there's variability in Y. So the conditional variability in Y given X, and then averaging over P of X, the outer part. So we'll look at both. Both are informative. And let's first look at the inner part. This is the expected loss over different values of Y. for a specific value of x. And you might say, you know, isn't y just a deterministic function of x? Well, not usually. In most problems, especially in sort of physical problems, you're going to have measurement noise, but you're also going to have unobserved variables that are, x is not going to completely determine y. There's probably going to be a stochastic relationship there. And so that's what this is capturing. If we go a little further, you know, what is the optimal predictor from this perspective? Well, if we have squared error, how to minimize it, the f function you should pick is the expected value of y. This is a simple result, many of us know it, but you're predicting what our function is trying to learn is the conditional mean of y as it varies in x space. That is the optimal predictor. The log loss is not so obvious, but it turns out it's actually going to estimate conditional probabilities. We wanted to do that, but we just sort of waved our hands earlier and said, let's make them numbers between 0 and 1. By recognizing, you know, essentially you do a little bit of math on this function here, the minimizing f are the conditional probabilities. This is very cool because we only train our models with, if you like, indicator functions saying this belongs to this class, this belongs to this class. We don't give it any probabilities, but in the limit, training with this loss function, it will produce conditional probabilities. And people noticed this early on in the 1980s, and then eventually led to this result. And you know, it's pretty obvious once you know how everything fits together. So minimizing the loss, in fact, is driving our deep learning model, if it's a deep learning model, towards learning expected values and conditional probabilities. So even though we never specified any probabilities or expected values in our setup of the problem, that's what's actually going on behind the scenes. And the other term here, p of x, the outer term, what role does that play? So I'll talk about that for a minute. So what we want to do there is we don't want to minimize just at some particular x value. We want to minimize average loss over the whole input space. That's what that expectation is for. So what will happen is we'll emphasize regions where there's a lot of data, images that have certain characteristics, where there's a lot of images of that type, high density for p of x, and downweight regions of low density. And important is that if our distribution of x's doesn't reflect the future where we're going to be using the model for prediction, then we're optimizing the wrong part of the input space. And to show you that, here's a very simple one-dimensional example. So let's say this is our problem. Here's our y values, and here's our x values, and here's our data, the red points. And let's say the true function that we don't know, we're trying to learn, the true expected value of y given x is this blue function. So we have very noisy data, especially in this region here. And the optimal predictor, let's say we're using squared error, is the mean of this function, which we haven't seen. It's hidden from us. That's what we're trying to learn. All right. So let's say the inputs are distributed in this fashion, and we can kind of see that from up here, that they're kind of centered around here. This is our training data coming from this p of x. So this is p of x, this is p of y given x in this direction. Let's say we're limited to a very simple model. So we're not doing deep learning in this picture for the purposes of illustration. We're just fitting a linear model. The true function is nonlinear, but we can get a pretty good fit, especially in the middle here where most of our data is. So we were pretty happy. Best linear fit. Now what happens if in the future, we were kind of given the wrong data? And this happens a lot. The data is from the past, things have shifted, our instrument is calibrated differently or whatever. And then we want to make predictions out here now in this part of the space. We had very little data to train on over here. Well, unfortunately, because of what happened, this was the model we fit, but this is the best model down here. If we knew somehow that we were predicting over here, this is what we would have fit. We could get great predictions in this region, but we're going to do much worse with the model we actually fit. And so, our predictions may be quite suboptimal. As a side note, if somebody were to tell me what Q of X is, even though I don't have data there, I could do some importance sampling and reweight the expected loss, the total loss, reweight these red dots to get a model that fits well over here. And again, that's something that comes from the connection between these empirical loss functions and statistical thinking. And one more point that I made earlier is the connection with likelihood also allows us to think about being Bayesian. And if you don't know much about being Bayesian, don't worry about it, but some of you are probably interested in this. So this is the loss function we had before. And on the empirical side of it, the kind of optimization perspective, you often add a regularization term, some function of theta that encourages the parameters to remain small unless the data suggests they should be large, keep them close to 0. And there's usually some strength for the regularization. Well, it's fairly easy to show, just to show that this is a negative log likelihood, this is a negative log prior, or can be interpreted in that way. And so if we have a squared penalty function here on our parameters, this is like a Gaussian prior. If we have absolute value, which turns out to be pushes things to zero faster, that's a Laplacian prior. You can go crazy with different kinds of priors. Dropout can be interpreted this way. And my grad student, Eric Nalisnik, a few years ago, wrote some nice papers on other variations of priors. So it allows you, again, to be Bayesian. Now, you might say, well, that's not really being fully Bayesian. So what does fully Bayesian mean? Fully Bayesian in deep learning means that you're modeling uncertainty about all the weights and then averaging over this uncertainty when you make predictions. And mathematically, given what I've told you so far, we could do this. We have priors. We can put them on the weights. We have likelihoods. But unfortunately, I have to tell you as of today, and probably for the next while, this is pretty much impractical. A lot of people looking at it, but to do it for these large networks, it really doesn't scale up well. So being fully Bayesian with deep learning, if you're a PhD student, there's an opportunity to make your name by doing something clever in that department. So a lot of research going on there, but not realistic at the moment. All right, story so far, and let's see, how are we doing on time here? Probably. Kieran, I can't hear you. So
you've been talking about 45 minutes.
So another 10 minutes is okay, or so?
10 minutes is fine. Yeah.
All right. So essentially what we've learned so far, just to summarize, is that we can set up our predictive modeling framework essentially as an optimization problem on thetas, and we can use very flexible functions for our f's. And this looks very much like a deterministic optimization problem. And this, what I've written on the slide here, there's no mention of statistics or probabilities or distributions, but implicit, what I hope I've convinced you, implicit are connections to likelihoods, expected values and conditional distributions. The input distribution PX is playing a role here, and that we can have Bayesian perspectives on our parameters and so forth. So there's really more going on behind the scenes. That one of the reasons I present this story is when you read papers about neural networks, they don't always make this connection. And I think it's useful to know if you're going to use these models and are wondering, deep networks, statistics, are they two different worlds? No, they're actually connected. For the last few minutes, I'm going to tell you about some limitations. And this is kind of a public service announcement that I always feel obliged to tell when I'm speaking to non-machine learning groups. So, there's a lot of positives about deep learning, very powerful tool, but I think it's important to realize it has limitations. So I'll run through a few examples. So one of the things we've been learning recently is that deep learning and deep learning models in humans are handling data very different ways in pattern recognition problems. So this is data from a well-known testbed for image classification, kind of low resolution images. These are the images that on the left that humans are uncertain about. I hope you can see my mouse still. Yeah, great. And they're ambiguous. It's very hard to tell what they are. They're blurry. They're supposed to be animals and objects. They're really, mislabeled images. The ones on the right are the ones that the model, a deep learning model, was most unsure about. And it's interesting because it's quite different to this class. These are the ones you might intuitively expect. It's hard to label them. Over here, you see parrots and horses and another horse and a cat. But for some reason, the deep learning model has a lot of trouble. It's highly uncertain about these particular images. And so we find that these models are often non-intuitive in what they do. I'll give you a few more examples of sort of where models and humans differ in how they do this type of pattern recognition. This is a recent paper a few years ago where they take, again, testbed images and ImageNet images and add noise and gradually ramp up the noise and look at how humans and models compare in terms of accuracy. So the y-axis is accuracy, and this is the amount of noise being added to these images. And what they found is that the deep networks, we focus on this one on the left, degrade very rapidly. They fall off very rapidly, and human classification is much less. In fact, at the beginning, with no noise, the networks are more accurate than humans. But as they add noise, the humans sort of degrade gracefully, and deep networks fall away. And this is a common theme that I'm going to emphasize in the next few minutes, that when you change the sort of regime of the data that you trained on, these models can degrade pretty rapidly. Some of you are familiar with these adversarial examples where you can change an image that looks exactly the same to a human by adding a small amount of random noise, but in the model space, it turns out you can completely change the classification label, and it's very easy to do this actually. So what's happening is it's pushing it across a decision boundary, and now it's considered an airliner. And obviously this is completely nonsensical to a human, but in the learned space for the classification model, this is what's happening. And in general, people have been found, this is nearly 10 years ago now, a paper by Max Welling and colleagues. Max used to be here at UCI. Here's a machine learning model trained to find people in images. So you run it on a data set where there's no people, and this is in Venice, there's just buildings, and it'll happily find what it thinks are people at all these windows. And so these models in the wild can be quite unpredictable. I think I'll skip over these in the interest of time, just saying some of these this is models that rely on, overly rely on texture and colors. So here it's really a dragonfly. The model is very confident it's a skunk, human, but it's picking up the color patterns. Here it thinks it's a banana. Here it thinks it's a dragonfly for some reason. Oh, it thinks it's a sea lion, really just a pot. And this was work by Dan Hendricks, who's a grad student at Berkeley. The accuracy, when he produced these images that really the model should have no problem handling, it went from 95% down to about 10% accuracy, huge reduction in accuracy. And so there is a sense that, and this is in computer vision in particular, the current deep neural networks are severely limited in their ability to generalize beyond the image data set used to train them. And I'm, again, telling you this to be careful about your training data and extrapolation. These models don't have any magic powers in extrapolation. They'll do well on the data you give them. Here's yet another example. We might say, well, what if we train our models so that at least when they get new data they haven't seen before, they can reflect their uncertainty, that they're not confident about the data. So here's a one-dimensional regression problem. Here's the training data. Here's the true function. This was purposely set up by me to make it a hard problem. But what I want the model to do is learn this relationship or some approximation, and then to be able to tell me out here that it's very uncertain. It doesn't know what's going on. So there are models that do this. Here I use something called a Gaussian process, which you can link in with neural networks. And the gray shaded region is the model's uncertainty. This is what it predicted. It does very well on the training data. And then, of course, it doesn't extrapolate because it doesn't know how to. There's no theory for extrapolation. But look at the error bars. They're way off. And the actual function is up here. So even though this is actually a very well-respected method, it completely underestimates its uncertainty. And this is very common. Models tend to be very overconfident. Here's an example from classification where this is sometimes called reliability diagrams. What we're plotting is the confidence of the model, the probability that it assigns to the class that it's producing as its label. So a lot of them are over here around 0.9. But then we measure the actual accuracy. And what you see is that the model is saying 0.8, but its actual accuracy is 0.6. So it thinks it's 80% accurate on images around here, but it's actually only 60%. And so this kind of convex curve here, where it's below what would be perfectly calibrated, is very common. We see it a lot in deep learning. I'll give you another example. That's one of my favorite ones. This came from 2015. Again, testbed data set, train a model. It's very good at classifying guitars and penguins, very impressive results. What if we give it images that are completely outside what it was trained on, artificial images? What does it do? Well, it's very happy to tell you that this is a guitar and this is a penguin. And that's really not surprising because it has a finite list of things it knows about, finite set of objects. But what's more worrying is the confidence. So it's very confident over here in guitar and penguin, but it's even more confident than it was here about the real guitar, that this is a guitar, and very, very confident this is a penguin. So this is actually is a real problem. A lot of people are working on this, including my research group and others at UCI, and it's a hard problem. It might seem like it's simple, but it's really hard. And it's also really important. These systems are getting used in autonomous driving. They're getting used in medical diagnosis. So it's really important that we understand the model tells us when it doesn't know what the answer is. It's not confident. And what's really going on here is, like in two-dimensional feature space, we're trying to extrapolate out beyond where there's data. So maybe the decision boundary is well modeled here with blue class and red class, but where we have no data, there's no way to know how to extrapolate unless you have some theory. And so in physical sciences, actually, you might be in reasonably good shape because you might be able to impose some theory on how to extrapolate beyond the data. You might say, well, couldn't we detect when we're away from the data just by doing density estimation in the input space? And people have looked at that. And in fact, Eric Nalesnik, who got his PhD here in my group, wrote a very nice paper after he graduated, where he did this density estimation with a bunch of different methods. And sure enough, the new data has a different distribution to the images in sample. These are the ones it was trained on. These are the other images. It can detect that. But the problem is it's on the wrong side. it's actually giving higher probability to things it didn't see. It says they're more likely. What you want is this histogram to be over on the other side. So these density estimation techniques, detection techniques, and anomaly detection techniques are very unreliable in these high dimensional spaces. A lot of interesting research, but again, stay tuned. All right, concluding comments. I think if you're a student or a researcher thinking about using machine learning, deep learning, you should, before you jump in, it's very cool to use deep learning, but just ask yourself, is machine learning appropriate at all for your problem? Maybe you don't have enough data. Maybe there's a theoretical model you could write down instead. And if you are doing machine learning, is deep learning the best approach? Again, it's very cool. It's the current method du jour that everybody is excited about. But simpler models sometimes work better on smaller data sets, or there may be statistical models that have better uncertainty properties, better calibration. And if you do then go and build a complicated deep learning model, do keep in mind generalizing beyond your training data. I hope I've convinced you that even with very sophisticated models, with a lot of people working on them in machine learning, extrapolating, generalizing beyond the training data is unreliable for the most part. One other point I want to make is that, let's say you're successful in all of that, and you build a model that really does generalize well, like for astronomy, it's going to do classification of images, and you want to put it in a pipeline to do things automatically, which is great, and people are doing this. There's a notion called technical debt in software engineering, which means you introduce a new feature, and the debt is to then you have a debt to fix everything else and test everything else. And this is a paper from Google a few years ago that made a really excellent point. They have, Google has applied machine learning all over the place. And they pointed out that this little black box in here is the actual machine learning code, the learn model doing something, making some very useful predictions, but it's surrounded by all these other pieces of software. So when you introduce this piece of machine learning code, you have to test and integrate it with everything else in an operational setup. So it better be useful. It better not be giving you a 0.01% increase in accuracy. It needs to be 3% or 10% to pay off the cost of integrating it and testing it. So that's a kind of a practical issue. To finish off, maybe the one thing you could take away from this is these deep learning models. Deep learning is really cool at how it does feature extraction in terms of these flexible architectures, has some very neat optimization ideas, but there's a statistical part, particularly sort of at the output of these models in terms of the loss functions, getting calibrated uncertainty and so forth, that a lot we can borrow from there. So deep learning has very impressive results, particularly in pattern recognition, where our signals are kind of low levels, images, speech, text, but there are blind spots, and just beware the hype. I will say this, even though this has been recorded by video, and even though many of my colleagues and friends work in industry, industry has a vested interest in these techniques. They want to sell you cloud computing. They want you to believe that deep learning is the solution to all of mankind's problems. Just be careful. They're kind of looking at the optimistic side, the commercial side of things. There's many foundational ideas. I hope I also, alerted you to that. Many of the foundational ideas of deep learning are grounded in statistics, and again, I want to, especially for students who are thinking of using deep learning, machine learning in general in their research careers, don't throw away your statistics books. Read some statistics books, understand those connections, and I'll leave with some of my favorites. Leo Breiman, who unfortunately has passed away, was a professor at Berkeley. He was onto this very early on. This is a great article. This is a great textbook, Friedman, Hastie, Chip Shirani. Anything by Mike Jordan, Tom Mitchell is usually good. And Brad Efron and Trevor Hastie, if you only want to read one thing, chapter 18 of their textbook, which is available online, is a great read. Very short, but a statistical perspective on neural networks. Thank you. I'll stop. I think I'm over time, so sorry about that.
No problem. Thank you very much, Padhraic.
Yes.
I think we're everybody.
Yeah, thank you.
So do we have questions yet? Maybe I could start with one. So somebody's asking, will we be able to access the video later? And the answer is yes. Domingos, how quickly will it appear?
If okay with Professor Smyth, later today even.
Sure, that sounds good to me. Go ahead.
Yeah, I want to mention that I got a few emails before the event asking if you'll be recorded.
Yeah. Yes. Okay. So in my course that I've been giving in chemistry, we do emphasize a bit we use the book, The Elements of Statistical Learning, for some parts of the course and emphasize the more mathematical aspects. So I'm very happy that you're going through this, right? So I have a question that comes up very early on in the course, and it's related to many of the things that you were saying, and it's sort of to do with this extrapolation versus interpolation idea. So in one or a few dimensions, we have a strong intuitive idea of what the difference is between extrapolation and interpolation. And when you show us a picture, right, our brain tells us when we're in the one area and outside of it. But in a very high dimensional space, sort of if you have a strict definition of interpolation, let's say, of your data, it's something this size, right? It shrinks to zero relative to everything. And it seems like so how do you even decide if you are extrapolating or interpolating?
I think that's a really good question, and I think the answer is we don't know. Those results I showed where they did density estimation on pixels and found that they were the wrong side, essentially assigning higher probability to new data. That's, I think, exactly the problem, is that they were in the interior of where the data was. And these newer images had lower complexity, and so the model was happy. So it's not a simple kind of extrapolating out. It's the geometry is just, who knows?
Exactly. So as soon as you get to 4 or 5 dimensions and way beyond, right, the shapes you can make are unimaginable, right? And therefore, how do you possibly know if you're inside or outside? Or
I mean, there's a lot of work on manifolds and representations and a lot of theoreticians, but it's really hard to know. It's these are, and I think, one thing maybe is that machine learning researchers like to kind of come up with universal answers to problems, which sometimes is a good thing, but sometimes is a bad thing. So what happens in pixel space might not be what happens in text space, might not be what happens at time series. And currently a lot of research is dominated with image data used as testbed examples. And so some of the lessons learned there might not actually transfer over to other areas, but you might have other high dimensional problems where maybe there's more hope, maybe there's more structure. Because natural images are, pixel space is kind of an unnatural space to think about. It's, as a high dimensional space. But other problems hopefully have a much more, maybe there's structure you can take advantage of. I'm definitely, purposely not answering your question, Kieran, because I don't know how to answer it once we go beyond a few dimensions.
It comes up quite a bit in this series, because one thing is, as physical scientists, a lot of what we do is extrapolation, because we decide a simple law is true no matter what, right? And so no matter what new data we're given, this law will always be satisfied. And that's about as sort of 180 degrees away from some of these statistical ideas, right? Because you're
or machine learning ideas, at least. And if you think of something like speech recognition or some of these machine translation, the goal in some sense is to go out and get as much data to cover the space as possible. And if you can do that and solve the problem once for speech recognition, you kind of don't have to keep going back. So Apple and Amazon and Google, Microsoft have, very good speech recognition systems, because they've kind of keep extending the data to different accents, different age groups, etc. And then you can think of some systematic variation of, if somebody has a cold or not, you can, but you're still kind of doing interpolation. He's saying, well, I have these two extremes. How is a speech going to sound in between, for example? So,
right. Yes. So then you can think of it as by adding so much data, right? And then
it's kind of the brute force approach. There is no real theory involved. By the way, Domingos, are we still on video recording or not?
Yes, we are.
We are. Okay, I'll be careful what I say then.
So do we have questions from the audience? I guess a lot of people had to cut away at 3 o'clock.
Somebody raised the hand. Nicole. Yeah.
Yeah. Hi, everyone. Thank you, Padhraic, for this really informative talk. I have a question about the format for your feature inputs. So I, for example, work with a mixture of vector data and raster data. And I'm just wondering if you think there's a particular benefit to trying to format all of your data into vector format to run some of these models, or if it would be better, and like say you have on the order of 2 million points with a bunch of features for each one, or if it's better to try to push them all into raster data, or if it really just depends on the problem.
So if I understand your question, Nicole, it's if your data is spatial in nature, should you keep it that way or should you just vectorize it? Maybe as a rephrasing. So I'll answer that question, then come back and see if that was actually the question. You know, what I didn't probably make clear, but many of you probably know, is that when we take pixels as input, it does just write them out as vectors. It doesn't respect the spatial, you know, for the most part. It doesn't have knowledge of which pixels are where in the image. So in fact, all those examples I talked about with convolutional filters and so forth, surprisingly, in a sense, the convolutional filter does have a notion of locality built into it, but there, you know, the input, there's no, you know, there's nothing special you have to do to produce these as inputs. The only maybe suggestion would be that if you have kind of low level, say pixel input, say from a remote sensing instrument, and then something that's more, I don't know, the current temperature or something that's more high level global, that you might want to put that into the model sort of towards the output, maybe at the very output layer, rather than at the input. It could get lost with all the pixel information down at the beginning, because it's really, you know, the pixels are very sort of perceptual low level input, and something like temperature or rainfall is, you know, it's going to play a different role in the model. So I'd kind of have the model do feature extraction on the pixel stuff, the spatial stuff, and then maybe towards the end in that last layer, pop in your temperature and rainfall. And your standard packages will allow you to do that if you play with them enough. But again, it's, you know, rather than just accepting the generic default way of setting the problem up in PyTorch or TensorFlow, you kind of craft a model that kind of makes sense. So I don't know if that answered your question, but we can probably chat about it offline.
No, that's really helpful. So in terms of maybe leaving the data in the original resolution, but ordering how they go into the model so you don't lose your really high resolution information. I think that makes a lot of sense. Thank you.
Now, since I'm on your committee and there's a meeting in a week or two, we can follow up.
Yeah.
Don't have to get into all the details for everybody, but it's a good question. Yeah, thank you.
Do we have more?
I have one thing. I might be totally off, but when I look at your slide on recurrent network, I couldn't help but to think of Markov chains. Is there an affinity, a connection there?
Let me just, actually, yes. I mean, it's very interesting. So I probably shouldn't have done this. I think we're getting close. Yes, here we go. I think one way to think about it is that in these recurrent models, these are deterministic connections. There's no distributional assumptions about probabilities. So this is a sort of a dense real valued vector that represents sort of the state of a system. It's not a distribution over discrete states. Or if you had like a Kalman filter might be the more close thing, where you'd have a state vector, but you'd have a Gaussian distribution or some other distribution over that state vector. Here, you're essentially just, if you like, just tracking the mean. There's no uncertainty about the disease. So it's a very interesting topic, and a little bit of work exploring kind of the interface of these recurrent models and more classical state space Markov autoregressive models. And there is a type of Markov assumption. I mean, it depends. You're saying Py is a function, you know, of, it depends on past y's, but only through this mechanism here, only through the hidden state. So in some sense, this is trying to summarize the history and break. A direct Markov chain would have dependence on the y's directly, and you're trying to get something that's a bit more powerful than that by extracting information from the history. So That was probably a bit of a roundabout answer to your question, but hopefully gave you a sense of that. Yes, there are connections, but training these models can be tricky. You know, these recurrent models can be not that easy to train, and the work here is quite empirical. You try them; if they work, great. If not, back to the drawing board.
Thank you.
Right.
Do we have any further questions for Padhraic? Yes.
There is something on the chat. Nadia Ahmed, finding annotated data, especially in remote sensing, the physical science can be very difficult to come by. Are there any unsupervised or self-supervised techniques that can be used to assist with classification? Can traditional physics-based models be incorporated?
A lot of good questions embedded in that that comment. Let me see if I can. So having human labels is time consuming for sure. So the you know, self-supervised for time series, you know, it sort of just means you get to see what happens next. You have a time series, so you automatically have yt+1 always to predict. So that makes sense if there's a temporal aspect to the problem. There are semi-supervised techniques where you label a small amount of your data, and then you have a lot of unlabeled data. The theory on that suggests that if there's no misspecification in your model, if you have exactly the right model, then that will work. But if there's any misspecification in your model, it can be unstable. So semi-supervised learning, even though in theory it should work, in practice it often doesn't work as well as you might think. So so that's a kind of a mechanism where you get a small part of your data labeled and then sort of bootstrap a model from that with a lot of unlabeled data. And then using traditional physics-based models, you know, I think there's a lot of interesting work there. Mike Pritchard in Earth System Science is doing some interesting stuff, you know, combining simulators with data. There's a lot of other people at UCI that know more about this than I do. So I think the answer there is yes, but in terms of details, it's a you know, I think we had a talk recently from Lawrence Berkeley Labs where people were, you know, combining simulators with actual data. The particle physicists, I believe, do this kind of thing. I'm hand waving, so my short answer is yes, but it's not easy to do because your observational data and your simulator might sort of be telling you different things, and how do you resolve them and so forth. So yes, agreed. Annotated data is difficult to come by, and you know, crowdsourcing is something people do. You put stuff up on Mechanical Turk, and if it's a problem people can visually or manually solve, you can create a data set that way. People do that with language and speech and things, images, things like that. So it could be an option, say for remote sensing, if you can visually see what the answer should be. Anyway, good question.
All right.
Okay, if there are no more questions, let's thank Padhraic again.
Yes.
Thank you for listening.
That was an excellent background, especially with the emphasis on the statistics, right? One other thing is that there's another book, Introduction to Statistical Learning, with one of the same authors, and I think 3 students or something.
Yeah.
That's also very good. Like,
you're right.
It's an easier version of
yes. I think what you're referring to is, I think Hasty and Chipchirani are on that other book, or at least one of them. Yeah. And then Gareth James at USC, and maybe Daniel Whitman and a few other people. It's kind of, yeah, it has a lot less math, and it's a good one to start with. I agree. So
exactly, yeah, it get you into it a little easier. Yeah,
yeah, good point.
Okay, so thank you very much, Padhraic, and we must catch up, right?
Sounds good. Yes, let's do that.
All right.
Okay.
Great.
Thank you.
Bye, everybody.
Bye-bye.
Bye.